So far in our discussions of graphing, we've considered data obtained from one variable, either categorical or quantitative, and we've learned how to describe the distribution of that single variable using the appropriate visual displays as well as numerical measures of center and spread. Next, we're going to be visualizing our association of interest by exploring the relationship between two variables. Recall that our basic research question is whether or not two variables are associated with one another. So is there a relationship between gender and test scores? Is there a relationship between the type of light a baby sleeps with and whether or not the child develops nearsightedness? Are the smoking habits of a person related to that person's gender? Or how well can we predict a student's freshman year GPA from his or her SAT score? Before we test our own association of interest with inferential statistics, first we're going to work on visually describing that relationship. It is important to understand that when studying two variables, each variable has a role to play. That is, a variable may either be a response variable, also known as the dependent variable or outcome variable, or it could be the explanatory variable, also known as the independent variable or predictor variable. At this point, I'm going to be asking you to impose a causal model on your research question and to designate which of your variables is the explanatory variable and which is the response variable. Note that we can only impose a causal model rather than actually testing for causation because we're working with what's known as observational data. In other words, the data sets that we're using are based on studies where the sample is simply observed rather than being manipulated or influenced in any way as it would be in an experiment. Even though we won't be able to be certain that the association we're testing is causal, for the purposes of exploring our question, it remains important to determine the role that each variable will play in our model. This role type classification can be summarized and easily visualized in this table. This classification serves as the structure for the rest of this course. You will find that it does not only help you to construct graphs, which we'll be working on today, but it's also the basis for selecting statistical tools that can be used to explore the relationship that you're interested in. That is based on the role and type of each variable, whether response or explanatory, and whether categorical or quantitative. So to get the hang of this, let's go back to some examples and determine which of the role types represents each research question. So if we want to explore whether the outcome of the study, the test score, is affected by the test taker's gender, we would designate gender as the explanatory variable and test score as the response variable. If we want to explore whether the nearsightedness of a person can be explained by the type of light that that person slept with as a baby, light type would be the explanatory variable and nearsightedness would be the response variable. Here we're examining whether a student's SAT score is a good predictor of their GPA freshman year. So the SAT score would be the explanatory variable and the GPA of freshman year the response variable. If we want to see whether a person's pass-fail outcome on a driving test can be explained by the length of time that they practiced driving prior to the test, time in this case would be the explanatory variable and driving test the response variable.
For my own research question, I have decided that smoking will be the independent variable and nicotine dependence will be the dependent variable. That is, I am interested in the level of smoking at which nicotine dependence is experienced. When we graph the association between two variables, typically the independent or explanatory variable is plotted on the x-axis, and the dependent or response variable is plotted on the y-axis. In my graphing decisions flowchart, the first question is what type is the response variable? Is it categorical or quantitative? For my research question, the response or dependent variable is nicotine dependence, which is categorical. Now I have to ask myself how many categories are in the response variable. If you'll recall, the nicotine dependence variable is coded as 1 for yes or present and 0 for no or absent. So in my case, I have two categories in my response variable. With two categories, the next question I need to ask myself is, what is the type of predictor variable? If you'll recall, my explanatory or independent or predictor variable is the number of cigarettes smoked per month. As we saw in the demonstration of the histogram, this is a quantitative variable. Since it won't be visually meaningful to examine a bar chart with a quantitative explanatory variable on the y-axis, we will need to bin that variable into meaningful categories. That is, in order to visualize the relationship that we're interested in, we need to add some data management that will allow us to construct a categorical to categorical bar chart. Returning to my program, I am interested in creating a packs per month variable. I already have the number of cigarettes smoked per month as an estimate created. In each cigarette pack, there are 20 cigarettes. So what I will need to do is take this variable and divide it by the number 20 in order to get an estimate of the number of packs smoked per month. In order to do this, I'm going to click Transform and then Compute Variable. The variable that I'm interested in creating, I want to call packs per month. And the numeric expression I want is for it to be the number of cigarettes smoked per month estimate divided by the value 20. Click OK. We will now see this variable created on the right. So, this is of course still a quantitative variable, but now I can more easily create groups based on the number of packs smoked per month. Let's run a quick frequency table. After examining the frequency distribution, I decide that I'm going to create groups that include those who have smoked 1 through 5 packs per month, 6 through 10 packs, 11 through 20, 21 through 30, and then 30 plus. To do this, I'm going to click Transform, Recode into different variables. I'm going to convert my packs per month variable into a variable that I'm going to call pack category. And then I will assign the values that I want. The first group that I'm interested in is those who smoke 0 through 5 packs of cigarettes a month. I'm going to give the new value 3, which is going to be the midpoint of 0 through 5. Next, I'm going to create a group of those who smoke just over 5 through 10. The mean value for this is going to be 7. I will do this for the rest of my variables. For the value 30 plus, I find, using my frequency table, that the median value for this group is going to be 58. Always remember that if a value is missing in the old value, you want it to be missing in the new one as well. Click Continue, then OK. If I rerun frequency distributions for this new variable, I should have 5 values: 3, 7, 15, 25, and 58. These are all midpoints for the categories that I've created. I've tried to retain as much of the quantitative features of the original variable as I could manage, but also assure that my graph will be interpretable now with an explanatory categorical variable. Moving back to our graphing decisions flowchart, now that we've collapsed our explanatory quantitative variable into categories, we're ready to make our categorical to categorical bar chart. For most graphing that we will do in SPSS, we will go to Graphs, Chart Builder. However, for this one, I would like for you to go to Legacy Dialogs and then Bar Chart. We will want to create a simple graph with summaries for groups of cases. The reason that I want you to do this is because our y-axis variable, tab12 mdx, is actually categorical. This is the easiest way to display the mean of a categorical variable in graphing. We'll select Other Statistics, Mean, and then place tab12 mdx into that variable. Our predictor variable, pack category, we'll put on the category axis. Hit OK. So here I have my categorical by categorical bar chart. I have my pack categories, or explanatory variable, on the x-axis, and the proportion of people with nicotine dependence along the y-axis. We can also see that these rates form a pattern. That is, the more cigarette packs smoked per month, the higher the rate of nicotine dependence. So, in a graphical way, we're already seeing that there seems to be a relationship between smoking and nicotine dependence, as I had hypothesized. What if I were interested in the association between ethnicity and smoking stage, and I had created a response variable that categorized my young adult smokers into 3 groups? So, non-daily smokers, daily smokers, and then those with nicotine dependence. You can see in this slide, I show the ethnic groups recorded in the NESARC codebook, as well as the 3 groups that I want for my smoking variable. I can certainly describe the sample in terms of these 3 smoking categories. As you can see here, I have a univariate bar chart showing that about 50% of the young adults sampled are nicotine dependent. About 30% are daily smokers without nicotine dependence, and almost 17% are non-daily smokers. However, to examine a relationship between this variable and my response variable, I really need to have only 2 categories. Either of the following are perfectly reasonable decisions. I could examine the association between ethnicity and daily versus non-daily smoking, or I could examine the association between ethnicity and nicotine-dependent versus non-nicotine-dependent individuals. So again, I need to collapse across these categories in some way. In either case, I'd need to add some data management to my program. If I decide that I want to collapse the response variable into daily versus non-daily smokers, I'd need to create a new variable called daily. As in our data management video, we know that we need to go to transform, recode into different variables. The variable that I'm interested in is S3AQ3B1. And I would like to create a variable called daily. If S3AQ3B1 equals 1, that is, the individual smoked 30 days a month, then the new value for daily I would like to equal 1. For the values 2 through the highest value, I would like to set to the value 0. And if there's any data that is missing in the old variable, I want to make sure that it is also missing in the new variable. Select Continue, and then OK. We now have a new variable called daily. After the data management, we should produce a frequency table for the new variable to check to make sure it is correct. This all looks good. I am now ready to graph my association between daily smoking and ethnicity. Go to Graphs, Chart Builder. We want a bar chart, so I will drag and drop that into the center screen. Our x-axis variable, or our predictor variable, is ethnicity, and our y-axis variable, or our response variable, is daily smoking. Select OK. If I examine this graph in conjunction with my codebook, I can see that ethnic group 3, American Indian or Alaskan Native, and group 5, Hispanic or Latino, seem to have slightly lower daily smoking rates than the other 3 ethnic groups. Back to our graphing decisions flowchart. Because our response variable was categorical with more than 2 categories, we needed to collapse it into only 2 categories. And because our explanatory variable ethnicity was categorical, we created a categorical by categorical bar chart. Had our explanatory variable been quantitative, we would have needed to bin or collapse that variable into categories before creating a categorical by categorical bar chart. So, from the 2 bivariate graph examples we've covered, we filled in the left side of our flowchart. Each example shows situations when our response variable was categorical. Let's now talk about the right side of our flowchart, when the response variable is quantitative. Again, changing my research question, this time I'm going to use an example from the Gapminder dataset. Here, I'm interested in the association between the percent of the population living in urban settings within each country and the country's rates of internet use. That is, the percent of people with access to the World Wide Web. In this slide, you can see the full description of these variables from the Gapminder codebook. So, in this example, both my response and explanatory variables are quantitative, and the graph of choice is a scatter plot. A scatterplot, by definition, is a graph of the plotted points that show the relationship between two quantitative variables. In a scatterplot, rather than displaying means or proportions of the response variable by the explanatory variables categories or groups, data for each individual's explanatory and response variable are plotted. Using the Analyze Descriptive Statistics descriptive command, we can see that for urban rate, the mean percent of the population living in urban settings is about 57%. The standard deviation is around 24%, suggesting that there's quite a bit of variability from country to country in terms of the proportion of the population living in urban settings. For internet use rate, on average, about 35.6% of the population across these individual countries have access to the World Wide Web. Again, the standard deviation is 27.8, so there seems to be quite a bit of variability from country to country. But is there a relationship between these two variables? To explore this question visually, we'll need to make a scatterplot. Returning to the program, let's go back to the graphics editor. Here we're going to select a scatterplot. Remember that our x-axis or predictor variable is urban rate, and our response variable is going to be internet use rate. Here we can add axis labels, as well as add a title. Once we've added those, we can select OK. While this graph is helpful, it may be more helpful to also add a best fit line. We can do this by double-clicking on the graph and then selecting Best Fit Line from the menu. This best fit line is helpful to categorize the relationship that we see in the scatterplot by fitting the observations to determine how the dots line up. That is, do they seem to line up in a positive or a negative direction, or with a positive or a negative slope? Given the increasing slope that we see here between urban rate and internet use rate, we can say that the relationship is positive. That is, an increase in one of the variables seems to be associated with an increase in the other. Here is another example from Gapminder, exploring the relationship between income per person in each country and the internet use rate. Again, if considering a linear pattern, the relationship seems to be positive. That is, the higher income is associated with the higher internet use rate. The strength of a relationship is determined by how closely the data point to the following form. We can see that in the scatter plot on the left, the data points follow the linear pattern quite closely. This is an example of a strong relationship. In the scatter plot on the right, the points also follow the linear pattern, but much less closely. Therefore, we can say that the relationship is weaker. The form of the relationship is its general shape. When identifying the form, we try to find the simplest way to describe the shape of the scatterplot. There are many possible forms. As we saw, a positive or increasing relationship means that an increase in one of the variables is associated with an increase in the other, and a negative or decreasing relationship means that an increase in one of the variables is associated with a decrease in the other, as shown in the central scatterplot. Not all relationships can be classified as either positive or negative. Further, if you can't plausibly put a line through the dots, that is, if the dots just are amorphic, then there may be no relationship at all. For various reasons, a scatterplot is sometimes limited in its ability to allow us to evaluate the relationship visually. Here I show a scatterplot for income per person by HIV rate among 15 to 49-year-olds. Since most countries have low HIV rates per 100 people, the dots on the scatterplot seem to clump in the lower left-hand corner of the graph. So to try to get a better sense of whether or not there is a relationship between these two variables, I'm going to have to categorize or group my explanatory variable. If I produce a frequency table for income per person, I can use this information to determine the 25th, 50th, and 75th percentiles, or quartiles. These will allow me to divide the countries into 4 ordered groups according to income per person. Once I create this new categorical explanatory variable, I'm ready for the last type of bivariate graph, that is, a categorical to quantitative bar chart. The steps are the same as before, using Chart Builder and then dragging the correct variables into the chart preview. In this bar chart, while we can see that there are clear differences in HIV rate based on income per person within countries, the relationship does not seem to be linear. Although I expected a negative linear relationship, that is, increases in HIV rate with decreases in income, you can see that this does not follow that pattern, as group 3 falls outside this pattern. So we've done it. We've worked through each of the types of bivariate graph, that is, a two-variable graph, highlighting when and how each should be used to visualize a relationship. Now just let me very briefly summarize. When examining a categorical to categorical relationship, we use a bar chart with explanatory categories on the x-axis and the proportions of our response variable on the y-axis. When visualizing a categorical to quantitative relationship, we use a bar chart with the explanatory categories on the x-axis and the mean of our response variable on the y-axis. Finally, when visualizing a quantitative to quantitative relationship, we use a scatter plot, in which each observation is displayed according to the variables on the explanatory and the response variables. Now you should use these basic guidelines, as well as the Graphing Decisions flowchart, to visualize the relationship between your variables of interest. Good luck, and don't forget to ask for help whenever needed.